So it's this one, right? N square log n log n squared. So we're trying to determine which one of them. Now, when we talk about complexity and we want to reduce them and figure out what is the dominant term, what we usually consider a term is something that is separated from the other ones from either addition or subtraction. So which means that in this case, this is one term, this is another term. We don't drop things within a term. So for example, like n squared log n, they come together as a group. So we can't say, okay, I just keep one n because the log n is not a part of it. So this whole thing, you either keep everything or you drop everything. So then we just need to compare between the two, right? So in this case, n squared log n is the same as n times log n. Now this one, n log n squared is the same as n times log n times log n. So now we are trying to figure out which one is bigger, so we can compare term by term. So this term is similar, so it's n and n. This term is similar, so then it comes down to the comparison between n and log n. So if n here is larger, because n is linear, log n is logarithmic, right? So then this one is going to be bigger. So then we can drop this, and we just need to keep this. So it will be O n squared log n. So Jonathan, is that a question here, or does it answer your question? Now, some of you may be wondering why we don't write the log, the base of the log, when we talk about the complexities. The reason is because any log of any base can be written in terms of a log of different base. So for example, if you have log 2 of n, you can actually write this as log k of n divided by log k of 2. Now the k here can be any number, as long as it's the same base in the numerator and the denominator. So log k of 2 for some constant k, essentially then it becomes a constant. So you can cancel this as far as the big O is concerned, which means that any log of any base is proportional to the log of a different base of the same number. And since we only care about the growth rate and we are dropping constants in the big O, so we usually ignore the base. So we just say O log n, for example. Okay, so we don't need to keep the base when we write for the logarithms. All right, so for the last one, so the last one is 10 to the 5 plus 10 to the 4 So Jonathan, which ones here are the constants? Can we drop the constants? Which ones? This one? Okay. Anything else? All right. How about this one? Drop or no drop? Drop this as well. All right. So these are constants. So then we are left with the log n squared and log n squared, right? So log n squared is the same as log n times log n. So log n squared is log n times n. Now in terms of log, you can rewrite that in terms of log n plus log n, which is equals to 2 log n. And the 2 here essentially is a constant. So you can drop the 2. So you're comparing 1 log n versus log n squared. So the square of the number is going to be bigger. So then we will keep this one. Right? Any further clarification about question 2 before we move on to the other parts? Right, so maybe before we move on, so let's talk a little bit about what is a constant. So let's say we have an expression like this, right? 2n squared. Which one is a constant? Which one? The first two or the second two? This one is a constant. So why is this one a constant and this one not a constant? So the reason why we consider the constant doesn't matter is because we are looking at the way that the complexity is growing. So let's say this is the function in terms of fn, right? Now suppose that I grow the n by twice. So which means that instead of fn, I want the input to be 2n. So now what's going to be the outcome here? So if the input is 2n, then I'll have 2 times, so the n here will be 2n, right? 2n squared, right? Which is equals to, so in this case it will be 8n squared. Alright? Now suppose that then I want to see the growth rate, so I will take the ratio. So what is f2n divided by fn? So I'll take 8n squared divided by 2n squared. So which means that the ratio is actually 4 times. Now that is essentially the growth rate. Now let's say I'm going to change some of these numbers. So let's say if my function is not 2n squared, if my function actually is 3n squared, right? So my f2n is going to be 3 times of 2n squared, so which in this case is going to be 3 times 4, so in this case is 12n squared. So if I take the ratio, f2n divided by fn is going to be 12n squared divided by 3n squared is still equals to 4. So changing this number doesn't change the growth rate. That's why we call it a constant. Because we are looking at, as we're increasing the n, what is going to happen. Now, as opposed to changing the first number, let's change the second one. So in this case, we're going to have 2n cubed, let's say, right? We are changing the second number to 3. So then f2n will be equals to 2 times 2n cubed, which in this case is going to be 16n cubed. So again, if you take the ratio, f2n to fn, so we have 16n cubed over 2n cubed is now 8 times. So the ratio has changed if we change the exponent. But it doesn't change when we just change the number there. So that's why we consider this a constant, but this is not. Alright, so we always think of complexity in terms of the growth rate of the function. How is it growing? If it is going to affect the growth, then it's going to affect the complexity.